Hello friends, this is the first of a series where we go through some short but nifty calculations that could be done on the back of an envelope. This is good practice to remind ourselves of the many useful results we often need while trying to follow some physics calculations in a book or paper. Grab a pen and paper and let's get started. Our goal today is to derive the surface area and volume of a higher dimensional sphere in Euclidean space, also known as a hypersphere. For this, we only need to know about Gaussian integrals and the gamma function. Let's begin with the Gaussian integral. We would need an n-dimensional Gaussian integral over the whole Euclidean space, which is no more complicated than a single Gaussian integral. We just need to take it to the power of n. Let's remind ourselves of the standard result of a Gaussian integral. Just ignore the integrand for a moment. We are left with a volume integral over n-dimensional space. This is an Euclidean space because it can be described by Cartesian coordinates with lengths and distances defined by the Pythagoras formula. In this case, r is the radial distance from the origin. Let's use the spherical coordinates for this integral. Since we are integrating over a function that depends only on r, we can integrate over the angular variables beforehand, and the volume element would look like this. Whereas n-1 is the surface area of an n-dimensional unit sphere, which is multiplied by r to the power of n-1 to give the area of a sphere with radius r, and by the thickness dr to give the incremental volume. Recall what defines the unit sphere. It is all the points enclosed by this surface defined by the Pythagoras formula. This equation is also a constraint, which is why the surface area has one less degree of freedom. N always refers to the dimensionality of the space where the hypersphere lives. Each degree of freedom scales up proportionally with the radius r. Therefore, multiplying the unit sphere area with r to the power of its degree of freedom will give the area of a sphere with radius r. The same rule applies to the volume. Note that the subscript always refers to the number of degrees of freedom of the area or volume. A familiar example is a 2D spherical shell in 3-dimensional space. The surface area is S2 and the enclosed volume is V3. Going back to our integral, and using the spherical coordinates, here we make a change of variable, replacing r squared with r prime. Now the integral in the red box should be familiar to some of us. It is the gamma function, another key ingredient in our derivation. The gamma function has this recursive property that is similar to the factorial. In fact, gamma n plus 1 is equal to n factorial if n is a positive integer. The gamma function is the extension of the factorial into the complex plane, that is, it can take complex numbers as its argument. Thus we have the surface area of an n-dimensional unit sphere. To make good use of this formula, it is convenient to know the value of gamma half. With this, we can make use of the recursive property of gamma to calculate all the values required for the denominator of this formula for integer n. From the definition of gamma, we would need to evaluate this integral, which is actually a Gaussian integral in disguise. Just change variable to x. Notice that this is the reverse of the previous steps in getting to the gamma function from a Gaussian integral. From here, we just get the standard value of the square root of pi. By the recursive relation, we can calculate gamma 3 over 2. This is required for the case of n equals 3, our standard example. Indeed, the surface area of a unit sphere in 3-dimensional space is 4 pi. With the surface area, it is a simple step to get the unit sphere volume. Hence, we have calculated the surface area and volume of a hypersphere using just the Gaussian integral and the gamma function. If you like this video, consider giving it a like and subscribe to this channel and get notified whenever a new video is ready. Thanks for watching.